Thank you. So anyway, it is a classifier. So does anybody have any questions about how this works? Because we spent a lot of time on discussing that in the videos.
Professor?
Yes.
Can I ask if naive rule and complete base the same thing, because the explanation in the video sounds the same?
Can you say that again?
Naive rule and complete base, is it the same thing?
Once more?
Naive rule and complete base.
I don't understand your question. Maybe you can type it in the chat.
Excuse me, Professor. I think she's asking what's the difference between complete Bayes and naive Bayes.
Ah, okay. What's the difference between complete Bayes and naive? Okay. Oh.
And naive rules.
Oh, and naive rules. Okay. Well, that's the whole subject of the videos. Did you watch the video?
Yes. The explanation sounds the same, similar.
All of them sound the same?
Not.
Which ones sound the same?
They use the majority of the class, right?
Okay, right. So that's true. That you can say that. That's right. So naive rule is really, we said, just 0R, right?
Yes.
Okay. So, and we know that 0R uses the majority class, right? So you're right. That's right. Okay, now next comes the complete Bayes. So somebody want to offer an explanation of the difference, because she said, well, they all use, and so the complete Bayes uses the majority rule. So that sounds right. In fact, it is right. But so what's the difference? Anybody want to offer an explanation as to what's the difference between naive rule and complete Bayes? Nobody?
Professor, if I just have a tiny idea, it's like the assumption of using conditional independence. Is that?
No, that's for the next.
Naive. Oh.
So the question is, what's the difference between the naive rule and complete Bayes? So there's 3 steps in this process, right? There's the naive rule, then there's the complete Bayes that changes it's a change from the naive rule, and then there's the naive Bayes, which is a change from the complete Bayes. So we're asking, what's the difference between the first 2 steps? No? Nobody got that? There is a difference. Although, if you watch that video, we did a little test on a modified golf data set where we limited the golf data set to only 1 input variable. So instead of the typical, I think, 4 or 5 inputs, we just used 1 input variable, that was humidity. And then we tried out complete Bayes with just that 1 variable. I think we said, suppose that it's humid, you know, or humidity is high, or whatever whatever it says, and so we tested it out, and what turned out to be true was actually, in that case, the naive rule and the complete Bayes gave the same prediction for whether they're going to play golf or not, the same prediction for the output variable. But that was just, you know, that just happened. Doesn't mean it's always going to happen, right? They're not always going to predict the same thing, but they could predict the same thing. Why not? But yeah, in that case, they did both. It turned out that the naive rule also predicted the same thing that complete Bayes. But that was somehow because of the nature of that data set, or the structure of that data set. In fact, that data set, though, I kind of made it up. I didn't keep the original weather data set. I just constructed a new data set, but I used the same names for the variables. I used humidity and play and not play. Okay, so anyway, but they aren't the same. They are not the same. Although, as someone said, they both use what? The same, this concept of the majority rule, or at least the words majority rule appear in both discussions, but they're not used the same way. Majority rule, you do hear that in the first algorithm, the naive rule, and you do hear it in the complete Bayes. I did say those words both times, but not in the same way.
Okay, thank you, Professor.
No, I didn't answer it yet. I'm waiting for an answer from other people. I'm hoping that somebody can give the answer. Okay, well, I think what I'm gonna do is, okay, so is it true that no one can give the right answer?
Professor?
Yeah.
I was wondering, does it include the conditional independence variable in, no?
Oh, well, wait, let's see. Maybe you could say it that way.
Because in the formula, that's the only difference that
Yeah, that's true. That's true, but yes, it does. But how do you explain that with the words that she asked the question in, which is that they both use majority rule? Okay, well, in this case, what I'll do is, I was going to give you a test on this today, but I think I'll hold off on that and let you contemplate those videos a little bit longer. And of course, you need to do the homework on those videos. That will be due, I think, on Sunday or Saturday. So I will hold off on the quiz for today, and I'll do it next time. And you should figure it out. You have to figure out exactly the question she said. That's sort of the perfect framing of how to think about these those set of videos. Is what is the difference between the naive rule, the complete rule, and the naive Bayes. That's exactly what you should be trying to figure out. Okay, so I'll have to ask you to go back and review those videos. Hopefully they're not too confusing, and make sure you understand. And don't forget you have to know the probability at the beginning too, including conditional independence. So make sure you understand that as well. Okay, so I'll leave it at that for now, and we will have a quiz on it next time. You'll also have to do the homework, like I said, that is related to naive Bayes. Okay, does that everyone understand for now?
Yes, Professor.
Okay, good. So let's go to today. I think we're going to talk about regression. And first thing I'd like to check is whether you can go to this particular website and sign up for this course for free, because I've always been able to do it, but I tried it yesterday and I couldn't find the free link. So I want everybody to try this, and let's find out whether we can do it or not. So let's go to Coursera. So let's look up, so I'll do this on a new browser so that I can, let's see, I'll do this on a private window. So let's all try and do this together and see if we can find this information. Now, I don't think I can even, well, anyway, let's go. So what we want to look up is type in Emily Fox and machine learning, regression, and Coursera. Best if you do it in this order. So type in Emily Fox, machine learning, regression, Coursera. And let's see if we can find this free link. Okay, so I'll say it once more. Emily Fox, machine learning, regression, Coursera. Now I'm gonna look for the result. So I get that, and I'm gonna change it to English. So I get that, and it's the machine learning regression Coursera course. Okay, does everyone find something like that? And then we go to that link. And you should get to a page that looks something like this. So has everyone found, is there anyone who can't find this?
Yes, Professor.
Yes, Professor.
I mean, is there anyone who cannot find it? Okay, so everyone found it. Okay, now, the question is, let's try this, enroll for free. Now, I used to see, well, okay, so now you have to enroll. So if you're not already enrolled at Coursera, if you've never used it before, you can enroll now. So just give a name, email, and password. And then I can't go any further because I've run out of emails to use. So I don't have another email to use. So okay, so I'll give you another few seconds to log in. And then can't seem to get rid of this. Try it again. Okay, now do you see this button here that says enroll for free? Does everyone see that?
Yes, sir.
Okay, now, okay, I want to be careful because I don't want you to say, well, anyway, what happens, or can I share, can somebody, let me let somebody share their screen. I want to see what you see, because what I see is not what I wanted to see. Let me see, where is this thing? Here. How do I do this? Okay, so, okay, can somebody share their screen? I want to see what you see.
Professor, I can share my screen.
Okay, great. Let's see. Okay, okay, let's see. Let me move that over here. Hold on one second. Oh, I move this. The options, exit full screen. Move that to here. Okay, you see it. Okay, good. So I couldn't see this on mine, but down at the bottom, does everyone see where it says audit the course at the very bottom? Don't click it yet, but just make sure everybody can see it. Does everyone see that?
Yes,
Professor.
Okay, so that's what you want. Don't click on the start free trial, because then they're going to ask you for your credit card and ask you for other stuff and make you pay eventually. So you don't want to do that. So click on the audit. I mean, if you pay, you can get a certificate and things like that, but for now, we're not going to do that. Okay, perfect. So click on that audit the course. Okay, and then you can just skip this actually. You don't need to do this. Okay, perfect. So everyone's can get there. So, all right, so now I'll go back to my screen. One person. Okay. And now I will share my screen. And the sound. So I want to go through some of this together, and I'll be making some comments as we go through it. And that will be, and then we'll do a little something else after that. Okay. Let me try this again. Share my screen. Okay, so I'll share my screen, which is here. Okay, and I'll go back to that page. And I will log in. I'm already logged in. Okay, so let's look at, I'll go to the course, which looks like this. Okay, and it's apparently it's a 6-week course, and there's some discussion forum here. Let me just click on that and see what that's like. So there are a bunch of questions and comments and so on. Might be interesting. And here's messages go to the first video. So, and then back to the overview, week 1. So the first thing is there's some videos, or sorry, reading, important update regarding this machine learning specialization. So they have a machine learning specialization. This is part of that. So this course is part of that group. And then reading the slides presented in this module, and video, which is a welcome. What is the course about? Outlining the first half of the course, outlining the second half of the course, assumed background, reading, software tools you'll need. What are the software tools you need? Python. Okay, but we won't go that far, so we won't need Python. And I'm not sure if you absolutely need that anyway. Okay, now we get to the section called Simple Linear Regression, and then there's Regression Fundamentals and video. So I want to start with this video. So the data set is going to be housing prices. So the task is going to be to predict housing prices. So let's watch this together. This lady was the I guess she still is at University of Washington in Seattle, which is a very good school as far as I can tell. And she's also now become the Amazon teacher, like Amazon, the company, teacher of machine learning or something like that. So she's, of course, Amazon headquarters is in Seattle. Okay, let's watch this together.
Okay, so for the first part of our course on regression, we're going to start with something that's called simple regression. And as the name implies, it's just a very simple form of regression where we assume that we just have one input and we're just trying to fit a line. Okay, but before we get to starting to talk about this simple regression model, let's just recall our task of interest, where our case study is discussing how to predict house prices. So in particular, we have some house that we want to list for sale, but we don't know the value of this house. And as we discussed at fairly great length in the first course of the specialization, what we're going to do in this case is we're going to look at other houses that sold in the recent past and look at how much they sold in different.
So what do we call that? What are we going to look at? We're going to look at other houses. So what do we call that? We call that the training data, right? We're going to look at training data.
Different characteristics of those houses and use that data to inform our listing price for our house that we'd like to sell.
Okay, let's watch this one.
So let's go through some of the regression fundamentals. What's our data? What's the model that we're going to use? And what's our task of interest? Okay, so the first thing is we're going to take all of our data, so all these houses that we looked at that sold recently, and for each one of them, we're going to record some information. And in this case...
So, okay, again, what data are we looking at? What do we call the data that we're looking at?
The training set.
Yeah, and from this picture, what do you think the training set consists of?
The price and
Area.
the area.
Right, the price and the area.
Price and area.
Right, so we only have how many input variables?
2,
Input variables.
5.
1, 2, 3, 4, 5.
No.
2.
2. What? I'm sorry, no, not 2. How many input variables do we have?
1,
1.
Right, and how many output variables do we have?
1,
We almost, I mean, it's very, 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 very rare that you have more than one output variable. Okay, but how many, once again, how many input variables do we have?
1.
And what is it called? Yeah, square feet or area, right. Square feet or area, right. And how many rows of data do they show on the screen?
5.
Right, so that's, but of course we obviously have more than 5 rows. It's just writing it like that. Okay, does everyone follow this?
Yes, Professor.
Okay, so the first thing is we're going to take all of our data, so all these houses that we looked at that sold recently, and for each one of them, we're going to record some information. And in this case, in the case of simple regression, where we're assuming that there's just one variable that we're using to predict our house.
Okay, so that's what simple regression. So we have multiple regression, and we have simple regression. And in simple regression, you only have one variable. So that's pretty limited, right? We've been dealing with many variables already, right? In our data science class. But in regression, you always start out with studying with just one variable. And regression is much older than data sciences. So regression was sort of the first data science algorithm. And when regression is taught, it's always taught first with, as simple regression, first with just one input variable. And then you go on to multiple regression, which means many input variables.
Price, specifically square feet. For every house, we're going to record how many square feet the house had and what the price was that that house sold for. And so we record this for each of our houses that have sold in the past. And this variable X represents the input to our model. Okay, this is what we're going to use for our prediction. And what's the output? What are we trying to predict? Well, we're trying to predict the price of the house. So that Y variable is going to be the output. So what's the difference between the...
Oh, by the way, which variables are numeric and which variables are non-numeric?
I think they're both numeric.
Both numeric.
Right, they're both numeric. We don't have any non-numeric variables in this example.
Input and the output? Well, the output Y is our quantity of interest. This is our goal. We're trying to predict the value of our house so we can list it for sale. And we're going to assume that we can predict Y based on X. So we can predict the value of the house based on the square footage of the house.
Okay, now in statistics, in regression, they always use, for the output variable, they always use Y. Okay, so please remember that. We always use Y for the output variable. Now, this is a little, okay, it's okay. Okay, I see now. Okay, anyway, and the input variable is X.
Okay, so I'm going to take my data and I'm going to plot it X versus Y, where X is the square footage of each house and Y is the sales.
Okay, now, did we? Yes, we did. Did you, well, did we do this in Weka? Did we make these kinds of plots yet? I don't. I think when we did some visualizations, we did some of this kind of, but the main visualization at the beginning of Weka, it's a histogram. It's not this kind of plot. Let's see what this looks like. This is going to be what we call a scatter plot. In other words, you're going to have a house, and you're going to say, oh, well, how big was it? Okay, well, square feet was this number here, and its price was up here, so we're going to put a dot there. So each dot on this picture is going to represent a house. Okay, so everyone get this?
Yes.
Each dot, we're going to have many dots on here. Each one is going to represent a house. And then if you want to know about that house, you just say, what's the X coordinate? That's the square feet. What's the Y coordinate? That's the price.
Price. So that's what this cloud of points represents. And we made exactly this plot in the first course of the specialization. So just to be clear, this circle here represents, let's say, the ith house in my data set. And that house had some number of square feet, xi, and some sales price, yi. Okay, so this is my data, and what my model represents is the expected relationship.
Okay, so models are a kind of relationship, and by relationship or model, we mean that we expect that there's some relationship between the X variable and the Y variable. So what do we mean by a relationship between two variables? Let me try this. Let me try this. No, that's not what I want. Let me show this. What do we mean by a here? Okay. Can you see my whiteboard?
No.
No, Professor.
You can't see that. I have to stop sharing and share again. Okay. Okay. Now can you see it?
Yes, Professor.
Okay. So what do I mean by a relationship between these two variables? Let me put that here again. So we had, what did we have on the x-axis? What did she have on the x-axis?
The area.
Area.
Area. And what did she have on the y-axis?
The price.
And then each dot, we said, represents
The data, the house itself.
the house. Each dot is a house. This is a house. This is a house. This is a house. Okay. So, so what does it mean to say there is a relationship?
When one variable changes, the other one changes.
Okay, between the two variables. What does that mean? So it means that, yeah, you could say as one variable changes, the other changes. But it's a little bit weak to say that. I want to say a little bit more than that.
Professor, can we say it's a positive correlation?
Well, maybe in this case you can say a positive relation, but I want to know what the word relation means.
The price is dependent towards the area.
Okay, right. The price, let's write, so how do I write that, by the way? What's a nice way to write that? You said the price, and then what did you say? Is dependent on the area. So what's a nice way to write that? I could write that in English. I could say the price is dependent on the area, but in math, how would I say that?
Proportional.
Proportional, okay, I could say that. That's good. Okay, but proportional is
We could
actually,
write it
no.
as a function.
Proportional means that it's only, proportional means this. Over, some k, right? That's a very limited, that doesn't express all possible relations. But I want to be more general than this. This means, when you write this, you mean this. Or if you want to say it this way, when you write this, you mean a k for some constant. So that's very limited. I mean, there are many other relations besides that. So I want something a little more general than what you said, proportional.
Is it like a function?
Yes. So when we say there's one, I mean, you could say this, that P is some function of A, right? Now that doesn't mean like a nice formula function, like it has to be, something you can write out really nicely, like x squared plus 3x minus 8 or something like that. It doesn't mean that. It just means there's some relationship. Okay, so that's one way to say it, is that. But another way, another way of thinking about it is, of course, what we mean is that if we know something about, if we know what A is, we can make some kind of statement about what P is. And if we know, so for example, in this picture, if we know that A is low, this is kind of low, and if we know B is high, then we, in this case, it happens to be that when A is low, we're going to say P is low, and when A is high, we're going to say P is higher. But anyway, it means that there's some kind of, we can make some kind of prediction based on knowing the value of A. Okay, does everyone understand this idea? Okay, so that's what we mean by a model. Okay, so it means that there's some relationship between the input variable area and price. Now, okay, so let's keep going. Let's see what she says.
Between X and Y. Remember, that's what we're trying to figure out, because if we have that relationship, we can use it for predicting the value of my house that I'd like to list for sale. Okay, so we're going to assume some relationship, which is some functional relationship. So I'm going to call this some function f of x. And
now it doesn't have to look like such a smooth, kind of nice looking shape like that. It could be different other shapes as well. But anyway, she just has to draw something, and that's what she's going to draw in there. So that's just a representation of the fact that there's a relationship. So the relationship or the model is that green line or green curve.
And like I said, that what that function represents is the expected relationship between x and y. So let's walk through this in a little bit more detail. So let's look at this house, or just to make this a little bit cleaner, let's look at another house here. Now I've reused the letter that I like to use. So I'm going to call this house, I'm going to re-annotate this. I'm going to call this house J. This is XJ and YJ. And the reason I'm doing this is because I is a special notation for the house that I'm interested in. And so now this house here that I'm looking at, I'm going to say that it sold for some value yi. And based on my model, what my model is saying is that I'm assuming that yi is approximately equal to f of xi, this functional relationship between the square footage of house I and its sales price yi. But I'm assuming that my model is not 100% accurate. You can easily imagine that there are errors in this model because you can have two houses that have exactly the same number of square feet but sell for very different prices. They could have sold at different times. They could have had different numbers of bedrooms or bathrooms or size of the yard or specific location, neighborhoods, school districts, lots of things that we might not have taken into account in our model. So our model is just what we're using as our belief.
So what are we taking into account in this model?
Just the area.
Just the area, right? We're just looking at the area. So she said there are many other things, of course, that the price will depend on, but we're only taking into account the area, right? Okay. So that's why we don't expect, even if this model is, that's why we don't expect everything to fall directly on this green line, right? It's the green line is what sort of the predicted value for the price, given the square foot down here, the predicted value will be up here, but this house sold for less than its predicted value. Does everyone see that it sold for less than its predicted value? Does everyone see that?
Yes, Professor.
Because the predicted value is the height of the green line and for a particular area. So if at this area the area for this house was here. So if we go up, the predicted value, the predicted price would be up here, but it didn't sell for that much. It sold for this. So there's some difference. Maybe we want to call that the error. Now, the question is, do we call it the error of the dot or the error of the green line?
The green line.
Yeah, I guess I'd say it's the error of the green line. But anyway, that's a little bit of a philosophical debate.
About the relationship for prediction, but it's not 100% accurate. There's some error. So the error, so just to be clear, this point here, this x, is exactly f of xi. It's the function evaluated at some xi value. And we're saying that our observations, which don't fall exactly on this curve defined by f, there's some error. So we'll call this error specific to house I. We're going to call it epsilon I.
Okay, so what is the what is the predicted value? Is that the dot or the line?
The line.
The green line. And so what is that? Is that, how do we denote the height of that dot? How do we denote the height of that dot? What's the notation for the height of that dot, the dot on the line? Right here, it's f of xi, right? That's the height on the line. Does everyone agree with that?
Yes.
Okay, that's the height on the line. And how do we denote the actual price? I'm sorry, no, sorry. Sorry, how do we denote the actual price?
H epsilon.
What?
How, like the one that says house epsilon.
Okay, she has a mistake here. Oh, no, she doesn't, sorry. No, not epsilon, no. How do we-
YI?
Yes, yi. So yi is the actual price, right? That's the height of this dot. But what's the predicted height? I'm sorry, what's the predicted price?
FXI?
Fxi, right? So there's a difference, right? Yi is the height of this dot, and the predicted price is the height of this dot, which is f of xi, right? So you need to get this notation clear in your head, otherwise you'll get lost immediately. So let me say it one more time. What is the predicted price? It's the height on this green line, and that would be written as f of xi, because this green line is f. So it's f of xi. Okay, what is the actual price for this particular house? What's the notation for that?
YI?
Yi. You must understand this. Should I repeat it, or does everybody understand it? If you don't understand it, it's useless to go on.
I understand it, Professor.
Okay, should I repeat it, or is it okay? If anybody wants me to repeat it, tell me now.
Could you repeat it again?
Okay, there's a brave person. Okay. Yeah, let me say it one more time. So there's two, first of all, do you see, can you tell me what the height of this is, this blue dot here? What's the notation for that height?
YI?
Or let me, yeah. Well, let's go over to this one. How about this one? What's the notation for the height of this dot?
YJ?
Yeah, yj, right? Yj is that. And she doesn't really make it that clear here. But the notation for the height of this dot would be yi, would be over here. And that's why she wrote yi here. Okay, she doesn't really make it clear. There should be a line with a yi there. Okay, is that clear?
Yes.
Yes.
So the height of this dot is denoted by yi. Okay, all right. Now what's the height of this dot? Well, where is this dot? It's on the green line. So, and where is it? It's above xi. So what's the height of the dot above xi on the green line? That's what we mean by f of xi, right?
Yes.
Okay, so there's two different things here. There's the height of this and the height of this, and the notations for these are yi and f of xi. Okay, so you have to get that. You have to know that what those two notations stand for. Okay, now is yi equal to f of xi? Is yi equal to f of xi?
No.
No, it's not. In other words, the model is not perfect, right? The model predicts up here, that's f of xi, but the actual price is down here, that's yi. So the model's not perfect, right? It makes a mistake, right? It makes some amount of error, right?
Yes.
Okay, and how much error is it? It's the distance between here and here, right? That's the error, right? Okay, so what are we going to use to denote that distance, that error? What are we going to use? What symbol? What does she use?
Epsilon I.
Yeah, epsilon I. Now, why do we need that I there? Because this has a different error, and this one has a different error, and this one has a different error. So we need the I there to say that it's the error for that particular house. Okay, is this clear?
Yes, Professor.
Go on.
So just to be clear, this point here, this x, is exactly f of xi. It's the function evaluated at some xi value. And we're saying that our observations, which don't fall exactly on this curve defined by f, there's some error. So we'll call this error specific to house I. We're going to call it epsilon I. So what our regression model is saying is that we're assuming that our observation yi is equal to f of xi, our expected relationship between x and y, plus some error. And in particular, we're treating this error as a random.
Okay, so what did she just say? She said that it's obvious. Let me go back to here. She just said that, so I'll draw in some something like she had. So I'll do something like that. Whoops. Anyway, so here's a dot. Let's see, here's a dot. Let me go back to this color, I guess. So here's this is let's call this xi. So this is what do I denote the height of this dot here?
FXI.
Right. But the actual price, I'm sorry, this is not supposed to be, this is not part of the data set. I just was noting this, where this is. This is not part of our data set. Maybe I'll make it a different color. How do I do that? Let me go back to here. Go back to here. Okay. And go back to here. Go back to here. You don't know how bad this stuff is. How bad it is to try and write like this. Okay. So we have this is f of xi, but the actual value is here. So what do we denote the height of this point with? What's the height of this point?
YXI.
No, yi. Okay, this is xi. This is the ith house. It has area xi and height yi, okay? But what does this mean? This is the predicted height, right? I'm sorry, the predicted price, right? Everyone understand that? This is the predicted price. This is the actual price, right?
Yes, Professor.
And this is the error. Epsilon I is from here to here, right?
Yes, Professor.
Okay, so we can say that the yi, the true height of this dot, yi, this yi here, is equal to what? F of xi. Now that's not correct. Yi is not equal to f of xi, right? Here's f of xi is here.
Minus EI.
Right, right. And then, but the height, so this is here. This is f of xi, right?
Yes, Professor.
Okay, but that, so I can't say that yi is equal to f of xi. That's not right. Here's yi, here's f of xi. They're not equal. So what is true? Yi is equal to f of xi plus epsilon I, right? Does everyone get that?
Yes, Professor.
Okay, now it could be minus, it could like, it depends, you know, it could be minus epsilon I or plus epsilon I. We won't worry about that. But it's, let's just say plus epsilon I. Okay, so that is that's what she just wrote, this. Now the question is, what does this epsilon term look like? That's an important question in statistics. And what we mean by that is, like, is it, if we take all of the epsilons, here, take all of them. So take the one for this one and this one and this one, and each one has a different epsilon. Like this is one epsilon here, the different epsilon here. This is a very small epsilon here, right? Does everyone know what I'm talking about?
Yes, Professor.
So if we sum them all up and divide by the total number of points, in other words, if we kind of average all the epsilons, so this epsilon maybe is a negative, and this epsilon is a positive, and this epsilon is a negative maybe, and this epsilon is a negative, and this is a positive, right? Do you get it? The epsilons that are above the line, we might call them positive epsilons, and the epsilons that are below the line, we might call them negative epsilons. Does everyone understand that?
Yes, Professor.
So maybe if we add them all up, we might get 0, or we average them all out, we might get 0, right? Does everyone understand that? Because you're going to get positives and negatives, they might cancel, right?
Yes, Professor.
Okay, so we kind of hope for that situation. We hope that the epsilons, when you sort of look at all of them together, they end up being 0. Okay, and actually that epsilon, people have sort of go into thinking about the epsilon a little bit more. Actually, they spend time thinking about what it looks like or how it behaves and so on. But let's go on.
Quantity, and we're going to assume that the expected value of this error, so this notation is the expected value. So we're assuming the expected value of this error is equal to 0. And
so that just means basically what I just said. It's like the average of all of them. That's basically what the expected value is. It's the average of all of the epsilons is 0.
What is expected value? Well, it's just a weighted average of over all possible values that error can take, weighted by how likely the error is to take each of those values. But what this is saying that our expected error is going to be 0, means that it's equally likely that we're going to have positive or negative error for any given house sale. So it's equally likely that our error is positive or negative.
So in other words, once we identify here's a square foot, and here's an area, so we predict that it's going to be on the green line, but we recognize there's going to be an error, and that error could be positive or it could be negative. In this case, it's positive. And what we're saying is it's equally likely that it will be positive or negative. Okay, that's part of like the assumptions of this procedure. That the error is equally likely to be positive as it would to be negative.
And what does this imply? This implies that it's equally likely that our observation, the specific observation that we get, is above or below this functional relationship defined by.
Okay, now she keeps using the word observation, right? Did you hear she said observation?
Yes.
What the hell does she mean by that? Sorry about that language. What does she mean by the observation?
The instances, the data, the house.
That's right. That's right. That's statistical language, and it just means the data, the actual elements of your data set. So when we say the observation, we mean the elements of the data set. So that's the dots. So let's go back and hear what you said about that again.
So it's equally likely that our error is positive or negative. And what does this imply? This implies that it's equally likely that our observation, the specific observation that we get, is above or below this functional relationship defined by F.
So what the hell was that? What did she say? This functional relationship. Oh.
So let's go through some of the regression fundamentals.
What did she say? She said this functional relationship defined by F. That's a lot of words. So what did she just say? She said that we expect that the observation will be, let's put it in our own words, not in not so many words. What did she mean? She said this observation will be what? Is equally likely to be what?
Above or below the function?
Yeah, above or below the function, or above or below this green line, right?
Yes, Professor.
Okay, but and she said it. How did she say it? She said this functional relation which we call F. Okay, that's right. It's this functional relationship we call F, otherwise known as the green line. So, so anyway, we're saying that the dot, the observation, is equally likely to be above or below the green line. Okay, that's what she was saying.
Yi is equally likely to be above or below f of xi. Okay, so I want to be clear that this is the model that we're using. This is how we're assuming the world works. And there's this very famous quote by George Box that says,
okay, now how many people have been following what's going on in the world with COVID-19? How many people have been following what's going on with COVID-19? I guess everybody, right? Right?
Yeah.
I mean, everybody is, because you all have to stay at home. So you must be following this. Okay, so you might have heard that they make predictions about what's going to happen, you know, how it's going to get worse and how it's going to get better. And they say there's a model that they're using to predict how well it's, you know, what's going to happen. Like they always keep saying, you know, it's going to, you might have heard the words flatten the curve. Have you heard that? Flatten the curve, right? So what they mean by flatten the curve is that there's a curve and they want to flatten it, make it flatter, right? But anyway, we're talking about a curve, right? It looks like, usually when you see these curves, they look like this, okay? So, and they want to flatten it. But anyway, so when you talk about a curve, you're saying that's what you think is what's really going to happen, or that's what you think is, that's your, what should I say? That's your model of what's going to happen, okay? And same thing here. It's not noise. Somebody's making noise. So that's your model. So this is what the model of reality, or the model of the price. But we say there's this model, but we don't exactly expect all the dots to fall perfectly on the model.
Essentially, all models are wrong, but some are useful.
So that's what they say about the COVID. They say the models, we don't, even the scientists who give them say, we don't expect them to be right. We just sort of might be able to use them. And so this is a famous quote by this, one of the most famous statisticians. His name was George Box, which I guess that's where they're getting that statement from, is from George Box. Let's go back a little bit.
Model that we're using, this is how we're assuming the world works. And there's this very famous quote by George Box that says, essentially all models are wrong, but some are useful. So what this means is no model is going to be exactly how the world works. It's not going to exactly predict how houses sell just based on square feet, or even if you incorporated other things as well. There are always different idiosyncrasies in how the world works. But models are going to represent some useful abstraction of the relationship between, for example, square foot and price that is useful for a task such as prediction. Okay, so I want to make it very clear that everything I wrote on the last line is just our belief about how the world is going to work, or maybe it's not even our belief, maybe it's just something that we're going to use because it's useful, as George Box said, or it can be useful. And we're going to talk a lot about how we assess how useful things are in this course, but we're going to hold off on that conversation for now.
Okay, so that was a very important discussion. So if you need to, you should go back and review it again. And definitely you need to know the notation that she was talking about there. Okay, let's keep going. Okay, so now she's going to discuss what model is good. Now, we've used, what machine learning algorithms have we talked about so far in our class?
J48.
J48, what else?
1R.
1R, what else?
0R.
0R, what else?
Naive Bayes.
Naive Bayes, complete Bayes, right? And okay, so that's enough. So have any of them been perfect? Have we ever seen 100% accuracy?
No.
No, right? So does that mean we're not going to use it?
No.
No, right? So you all are happy with not having perfect models, right? Right? You don't think you have to have a perfect model. You know, how about, Google does a speech recognition, right? Is it always perfect?
No.
No. But do you use it anyway?
Yeah.
Yeah, right? So model doesn't have to be perfect for us to use it. I mean, everybody wants to use Google voice recognition or whatever other voice recognition, and even if it's not perfect, right? So the model doesn't have to be perfect in order to use it. So what did that guy George Box say? He said, what did he say? I forget. What did he say?
Essentially, all models are wrong, but some are
Okay.
useful.
Thank you. Essentially, all models are wrong, but some are useful. Okay, so we agree with that. Or you behave like that all the time, right? You're perfectly willing to use imperfect models, right? Okay, so so you're practicing what he observed. Now, the question is, so and you can imagine, of course, each algorithm that we've discussed will generate some different model, obviously, because they all give you different results. They all give you different accuracy rates, so they're not the same models. So all these algorithms generate different models. Well, the same thing here. In this scenario, the type of model we're going to generate, we could, come up with many different models. And she's going to discuss now the pictures of different possible models. Okay, and you can see in this graph, in this screen right now, you can see two different models, right? So, we can have all different kinds of pictures, and each one would be a different model, just like we've been discussing many different algorithms, and they're all generating different models. Same thing here. We could generate, or we could get or picture many different models. That's what she's going to discuss now.
Here, this is our S. My price increases at the same rate as I'm increasing. Okay, so the first regression task that we have is we have to figure out what model are we going to use. Are we going to assume that there's just a constant relationship between square footage and price? That means.
Okay, now that's a very weird model. Why is that a weird model?
Because the price of the house will be the same regardless of the square feet of the house.
Right, exactly. This model says that no matter what the square foot or the area of the house is, we're going to predict the same height or the same price for that house, right? Everyone see that?
Yes, Professor.
Yes, that's it.
Okay, that's what this says, right? It says no matter what the square foot, we're always going to, if the square foot is here, we're going to predict this price. But if the square foot is here, we're going to predict this price. This is the same price. So we're going to predict the same price no matter what the square foot. By the way, does that remind you of anything? Does that remind you of anything, any algorithms we've studied?
Is it 0R, Professor?
Yeah, it's 0R, isn't it? It just occurred to me now. I didn't ever make that connection before, but that's 0R, isn't it? Because 0R ignores the input, right? Ignores all the input variables. In this case, there's only one input variable, but it ignores all the inputs, right? So it just gives you the majority, which could be, it's just the same thing for every, no matter what you input into no matter what case you look at, you always get the same prediction. So this is kind of 0R in a numeric setting. These variables are numeric, but for 0R, we're talking about not a numeric output variable, right? When we did 0R, what kind of output variables were we considering?
The majority class.
Yeah, the majority class. The key word is class. So when we're using the word class, we're talking about what kind of variable?
Output.
What kind? Is it a numeric variable or a non-numeric variable when we use the word class?
Non-numeric.
Non-numeric.
Non-numeric, right? Right? I told you in for your projects, you have to use what kind of output variable?
Nominal.
Nominal, right? Non-numeric, right? Right? And when we talk about 1R, I'm sorry, 0R, we said choose the majority class, right? 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 Isn't that what 0R is? It's choosing the majority class, right?
Yes, Professor.
So class means what kind of a variable? You don't use the word class if you're talking about numbers. You use the word class if you're talking about nominal variables, right?
Yes, Professor.
So when we talk about 0R, we're talking about a nominal output variable, right?
Yes, Professor.
But what is this, is in this scenario, is the output variable nominal?
No.
No, it's price, it's a number, right? So it's a little bit of a different situation, a little bit of a different scenario. So it's a little different than 0R, but basically it's the same thing. We're predicting the same thing no matter what the input. But in this case, it's a price, so it's a number, not a class. Okay, but except for that, it's the same thing as 0R. Do you get this?
Yes, Professor.
Okay, so this is obviously not, you know, the most interesting model that we could come up with, right? Because it just says, no matter what the area, predict the same price. That's you know, obviously not so great, right? Like if the house is, you know, as big as a Tokyo one-person apartment, predict that it's, you know, it's going to be a certain price. And if it's a big, huge Tokyo apartment, it's going to be the same price. That obviously not going to work too well. Okay, but that's what she's showing here. The first thing she's showing.
Okay, so the first regression task that we have is we have to figure out what model are we going to use. Are we going to assume that there's just a constant relationship between square footage and price? That means regardless of the size of the house, we're expecting every house to sell for the same amount. Well, that's probably not a great model. Are we going to assume that there's some linear relationship? So as I increase square footage, my price increases at the same rate as I'm increasing square footage. Or am I going to assume that there's some quadratic fit or some higher order polynomial fit?
Okay, what did she call this one?
The same rate as I'm increasing square footage? Or am I going to assume that there's some quadratic fit or some higher order polynomial?
Okay, what does she call this one?
Same rate as increase.
No, the word she used, what is the word?
Square footage, my price increases at the same rate as I'm increasing square footage? Or am I going to assume that there's some quadratic fit or some higher order polynomial fit or the...
What did she call this?
Quadratic.
Quadratic. What does that mean?
A curve function.
Quadratic. What does that mean?
A curve function.
Square function.
Y equals ax squared plus bx plus c. That's called quadratic, right?
Yes.
So what are the, so far we said, whoops. So far we said you could use straight line, right? So that's y equals, say, 10, right? This might be some constant 10. Okay, that's one choice, one kind of model. Next one she said is
Linear.
linear, like that. It's y equals ax plus b, right? That's linear, right?
Yes.
And she said, no, maybe we could go more complicated. We could go like this. Y equals ax squared plus bx plus c. In other words, this would be a parabola. Okay, maybe we can do that. Or maybe we could go better. I mean, more complicated. Y equals let's say ax to the 5th plus bx to the 4th plus cx to the third plus, up to whatever, right? So that might be like that, okay? So maybe we, right? So we could say that we're going to limit ourselves to this model. Or we could say, no, we're going to let ourselves use a slightly more complicated model. Or we could say, no, we're going to let ourselves use a slightly more complicated. Or we could say we're even more complicated, right? Now, the more complicated the model, the harder it is to sort of work with it in some ways, but maybe the more accurate it is, right? If you allow, suppose I had this data. So if I have to fit a straight line, I'm not going to be able to touch all of those points, right? But if I use a parabola, I might be able to touch more of the points. And if I'm allowed to use a curve like this, I might be able to touch all of the points, right? So I could make it, really complicated and get a perfect fit, right? But it's going to turn out that we're not going to do that. But anyway, that's what she said. Let's keep going.
Are we going to assume that there's some linear relationship? So as I increase square footage, my price increases at the same rate as I'm increasing square footage. Or am I going to assume that there's some quadratic fit or some higher order polynomial fit, or the list of models I can consider is very long, and that's what this course is partially going to be about, is exploring different options that we have for models of our data.
Now, most of the models that we've discussed so far in our class are not between numeric variables. Okay, this model is about numeric variables, right? The square foot is numeric and the price is numeric. So when you have different scenarios, you work with different machine learning algorithms. So we had J48 is not for this kind of situation, but this is not for J48 either. I'm sorry. Yeah, this doesn't work for the kinds of scenarios that J48 works with, but this works for numeric and numeric. And so we're discussing now what kinds of models we might consider when we're looking at, numeric input and numeric output.
Okay, so one task is, out of the space of all these models that we might consider, which is the one that we should use for a given data set and task?
So she said, out of the space of all the models, she just means what? Out of all the possible models, which one is good? She calls that the space of all the models. Okay, that's a kind of mathematical term or way of discussing it. But anyway, it's just, out of all the models, which one should we use?
That we have. Okay, but now let's assume that we have selected the model we're going to use. In this case, here we're assuming that we're going to use just a quadratic fit. So
quadratic.
Assume model.
So the first task,
f of x.
The first task before was to decide on which kind of model we're going to use. The second task now is once we've chosen a type of model, so we're going to allow ourselves to go quadratic. We're not going to go higher order than quadratic, but we are allowing ourselves to go quadratic. Once we've decided that, so for a given model, like a given type of model, we want to find the best quadratic model to fit this data. That's what she's saying. We're going to decide what type first, and then try and fit from that type, try and fit the data.
X is a quadratic function. Then our next task is going to be to estimate a specific quadratic fit to the data. Okay, so a model just specifies the form of something.
So she said a model just specifies a form. So in other words, going to here, so we have our data. we have our data and we say, okay, we're going to allow ourselves to use quadratic. Okay, now that means what? We're going to allow ourselves to do ax squared plus bx plus c, right? But now we have to decide what a, b, and c, because there, you know, we can go, there's so many different quadratic models, you know. We could have a parabola that goes through, you know, that looks like that. We could have a parabola that looks like that. We could have a parabola that looks like that, right? There are many, many different parabolas. We have to decide which one. That's what she's focusing on now. In other words, what is the A, the B, and the C, right? So we're limiting ourselves to quadratic models, but then we have to estimate these things, the A, the B, and the C, or we have to decide what the A, the B, and the C are.
Estimate a specific quadratic fit to the data. Okay, so a model just specifies the form of something. It's going to be defined in terms of some set of parameters, and then we're going to have to estimate what the specific fit is from the data. So for example,
and she's kind of using the word model like I've been using the word machine learning algorithm. So we decide on a specific algorithm. We're going to use J48, but then we have to figure out the specific J48 model that actually works for our particular data. So that's what she's saying. When she says we're going to choose a quadratic model, that's like saying, oh, we're going to use J48. No, we're not going to use J48. We're going to use Bayes' algorithm. No, we're not going to use Bayes' algorithm. We're going to use, you know, some other one that we haven't discussed yet. So we're going to decide regression and quadratic, and then we have to estimate the parameters for that quadratic. In other words, we have to find the A, B, and C.
Here, this is our estimated quadratic fit, and we'll call it f hat of x. This is our estimated function that's fit from our specific data set. Or this is another function that we could have fit, and we'll talk about the way in which we're going to fit functions to data.
Okay, so let me just make the one last point here because we have to finish. So how many orange lines are there in this picture?
3.
3, right? And how many green?
1.
1, right? So what they're saying in this picture is the green is the real relation, the so-called real relationship between square feet and price. But remember that how many dots do we have here approximately? Let's say we have 20 dots, okay? But those dots, what in statistics, statisticians will call that just a sample of all possible dots. In other words, there's actually millions and millions of houses, and we only have a few in our sample. So we're going to use that sample to estimate our model. We don't expect it to give us the true model, because the true model is if you had all the data. But we don't have all the data. So our data is going to have some randomness in it. And so it's going to generate a model which is not the actual true relation. Now that sounds like a lot of kind of weird ways to think about things, but that is definitely the way this subject is presented. Okay? So the green line represents the true relationship. You can think of that as the relationship if you had all the data, what would you get? But we don't have all the data. We only have we only have 20 houses here. And we're going to use that to guess at our model. So we're not going to get the real one. So that's what all those orange lines are. If we had one set of data, we'd get one orange line. If we had a different set of data, we'd get a different orange line. If we had another set of data, we'd get another orange line. Now, the last thing I want to say is very important notation, and that is this notation, y hat. So let me go back to this. I keep doing that. Let me see if I can do this. Okay, let me go back to this, and this, and this. And, oh, sorry, that should be black. I'll use for them. I'll draw the line model purple this time. I meant to draw it green. Okay, there's the model. Now, what is, so here's it. Let's call this the ith house. The ith house. So what's this? X what?
xi.
And what's, and this, the height of this is what?
yi.
yi, which is over here. Yi, right? And what do we call the height of this?
Epsilon I.
No. Epsilon I is here.
Oh, fx.
Right. F of
xi.
xi. So over here is f of xi, right? Everyone agree with that?
Yes, Professor.
But I put that on the y-axis, right? Right? So I want to give it a y. I don't just want to leave it as f of xi. I want to say it's some y. But I can't say it's yi. That's wrong, right? Yi is down here. So I can't call it yi, right? We call it yi hat. So whenever, so in statistics, this stands, remember in confusion matrix, we had something like, I forget which goes which, but maybe we had the predicted up here and we had the actual here. I forget if it was that way or the other way around. Remember the confusion matrix? Right? So we have the predicted value versus the actual value, right? So this stands for the predicted value, and yi stands for the actual, and yi hat is the predicted. We can also call this f, well, I don't know, I forget if we do that. But I think she just did that. She called this f of xi hat. But anyway, this, what's the difference between yi, that's what I want you to know. What's the difference between yi and yi hat? So here's yi, and here's what we call yi hat. Okay, does everyone understand? So yi hat is what? The predicted value of the height, okay? Does everyone understand that?
Yes, Professor.
So yi hat is not, yi hat is not yi, right? Yi is the actual height, and yi hat, we've been calling it f of xi, but it's also called yi hat. Yi hat is the predicted value, predicted in the model. Okay, so yi hat, is it equal to yi?
Plus error.
What? Are they equal?
No.
No, not equal, right? I mean, they could be equal, maybe. Maybe the prediction is perfect, and then they would be equal. But in general, yi hat is not the same as yi. Okay? In fact, I guess we could say yi hat is equal to yi plus epsilon I. Okay? Okay, that's all for today. So this is statistics. This all this notation, yi and so on, f of xi, and all of that, epsilon I, it's all statistics, okay? But statistics is the beginning of regression, of data science, and the concepts from statistics run through data science. If you don't know them, you're kind of lost when you're reading things about data science, because we'll often use these symbols, you know, sort of assuming that you've studied statistics already. So it's important that we learn all of this stuff. Okay, we learn these symbols and what they mean. Okay, so we started that today, and we will do a little more on this later. Okay, so you'll have more homework. You have you should definitely go through the videos on Bayes again. Maybe twice more. You should go through them, because you don't get it the first time. It's not so. It's kind of complicated, kind of like a symphony. You have to, you know, there's a lot of pieces moving around there. So you have to go through it a few times, and then we'll have that test on that. Okay, that's all for today. Thank you for coming. Sorry.
Thank you, Professor.
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 Thank you.